Please tell us about the increasing complexity of expansion decks.
Will do. So, can you hear me?
Yep.
Yeah, cool. So, my name is Marcus, like Christopher said, and today my plan is to talk a little bit about the increasing complexity of our expansion decks, talk a little bit about the challenges, and propose some solutions. And some of the problems that or challenges I'll talk about, I also discussed in the blog post on Monday. So let's see if I can change slide. Yes. So for anyone that doesn't know about the Crazyflie deck subsystem, I'll do a quick walkthrough of it. So when the initial Crazyflie was released in 2013, maybe, we put a small expansion connector on it because we wanted to have a possibility to expand the platform with additional hardware after the release. The expansion connector wasn't that good, like mechanically. It was a connector that you had to solder small wires to be able to connect stuff. So when we worked on the Crazyflie 2.0 in 2014, we really wanted an expansion connector where it was easy for people to add additional hardware. We understand that we can't carry everything we want to, so customers will have to customize the platform. Like some people might want some decks, some functionality, others might want other functionality. So to achieve this, we put in the current deck connector, 2 rows of connectors. We put a 1-wire memory on each deck for automatic detection. So at boot up, the Crazyflie will know what decks are connected. You can connect multiple decks simultaneously. I think up to 3 now. The limit here is both weight, but also the number of pins used by each deck. You can mount them on top and bottom, and they contain a variety of buses, so you can interact with the hardware on the expansion decks. So there's I2C, SPI, there's 2 UARTs. There's also various other signals like wake up. It's possible for the decks to wake the Crazyflie up from sleep. The 1-wire, some GPIOs. There's 3-volt power from a Crazyflie with a few hundred milliamps of power budget. And there's also VCOM, so power from a battery, which the more complex decks use. So they have their own regulators to make their own 3 volts on the deck, and they use VCOM instead. USB to get the USB power and so on. So there's a lot of different signals, a lot of capabilities on this expansion connector. And we started out with a few decks, but today we have lots of decks, varying complexity. Some of them are very, very easy, just to solder different solder an LED on, for instance, to do some prototyping. And some of them are quite complex, like the AI deck that contains Wi-Fi, camera, and 2 microcontrollers. So there's a wide range of decks. Some of our customers also make their own decks with variations of hardware or combinations of what we've made before. So, like I said, so there's a wide range of different decks. Some are quite complex. And some of the challenges that we have seen now after almost 10 years with this expansion connector is that it's getting a little bit tight on the pins. So like I said, there's different buses that we can combine, but depending on how you combine the decks, you might be limited. There's also the problem of resource sharing in STM. So DMA, for instance, DMAing on the different buses might be a problem. Bus arbitration and performance. So some decks use the same bus, like multiple decks might use the SPI bus, and this might be limiting in performance. And the last one, but not least, is when we start putting microcontrollers on the decks, something that it wasn't really 10 years ago, we didn't think we were going to do this. So for instance, like the AI deck that even has 2 microcontrollers. So I'll go through the challenges a bit more in detail. So first one is the deck combination and pins. So as you see here is illustration showing the expansion connector. So 2 pin, 10 on the left, 10 on the right. So you can see there's 2 UARTs, for instance, there's SPI, there's also I2C, there's a few GPIOs and various powers. But as you can see, like if you want decks that have the UARTs, for instance, which is something you can't share between decks, or it's hard, then you start running into problems because there's two UARTs. So then we try to be smart when we design the decks, saying that, okay, this deck uses UART 1, for instance, and something that you maybe wouldn't want to use together with this deck will use UART 2 to avoid any conflicts and give as much configurability to the users as possible. So here is a table where you see the decks on the left. On the top, there's the different buses, and each row you see what pins the decks use. So you can see, like on the top one, the lead ring deck, for instance, uses IO 2 and 3 to do a PWM. The next one, the Qi wireless, doesn't use so much. Micro SD uses the SPI bus, you can see, and there's one chip select on IO4, and then the CS in parentheses is where you can solder and select different chip selects. Because as you can see, then quickly, like so some of the stuff will be hard to use together. So the big quad deck, for instance, doesn't work together with a lead ring deck because they both use IO2 and 3. So this is the kind of problem that I mean when I say like the pin resource. The local positioning deck together with the lighthouse deck on UART 1 also conflicts and so on. And I mean, it's not possible to, we try our best to come up with different configurations, but I mean, there is a limited amount of pins. The next issue that I talked about is the resource sharing, like the DMA. So even if we can split things up on different pins, something that we've seen sometimes is a problem is when we start using DMA for the different buses. So even though we're on different pins, they are interconnected for the DMA. So some of the stuff here I marked. So some of the stuff like the SPI for channel 0, and the UART 3, for instance. These two collide. So even if you're on different pins and you can use them, if you want to use DMA for both of them, you can't, because they both use stream 2 and 3. And this is something then seen from the bolt. And the next one is like timer 2 conflicts with UART2, and this is also used by the bolt. And it also conflicts, we can see UART2 and timer 3 conflicts. So UART2 is one of the UARTs on the deck, and timer 3 is the timer we use, for instance, for the lead ring. So, and the lead ring needs to be DMA'd, which means that when we connect the lead ring, we can't use the DMA for UART2. So even if we're on different pins, we still share some of the DMA streams, for instance. Yes, the next thing that I mentioned was bus arbitration. So like for SPI, we have some SPI decks, and they work well together. We've worked on trying to optimize the performance of these. So you can imagine combinations where you have the LPS, you have a local positioning system, you have SD card, and you have a flow deck, for instance. So all these 3 decks use the SPI bus, which means they have to share it using the chip select. And it's possible, but if you look here at the screenshot, like the 2 line 3 and 4, this shows the chip select for the SD card and the LPS. And if you look at this, you can see that it's, I mean, it is being shared, but it's pretty packed, and potentially we might run into problems here if we add more SPI decks. Yep, and the last one, then the microcontrollers on the decks. So here are some pictures of the decks we have, which has microcontrollers. We have the AI deck with 2 microcontrollers and a Wi-Fi. We have the Lighthouse deck that has an FPGA on it, and we have the Qualysys Actimeter deck that has a microcontroller on it. So here we start having some issues with communication. So we need to communicate with the decks and the Crazyflie. We need to communicate, like, of course, doing normal business, but we also need to communicate for bootloading, for instance. And also having tools during development. So if you're working with this and you have multiple microcontrollers, you try to debug one microcontroller, you break it. How does the others respond? Like, does communication break down and so on? So there are some challenges here having microcontrollers on the DEX. So the proposed solution. So this is something that we've been discussing a lot, from time to time around the office. Often we end up in front of a whiteboard discussing different solutions to these challenges, depending on what prototype or new deck we might be thinking about or working on. And the solution I'm proposing here is, proposed solution. Let's see, maybe it's not this, maybe it's something similar. But something we've been discussing a lot is then trying to meet these challenges by moving more logic out onto the DEX. So for instance, in the resource sharing that we discussed with the DMA, we're using up a lot of resources on the STM to just do the DMA for the LED ring, for instance. This could have been easily done with I2C on the LED ring and then do the LED control on the LED ring, for instance, which would have freed up this DMA channel stream. Another thing is the bus arbitration then. This is also something that we could work on by moving the microcontrollers onto the DEX. So, or moving a microcontroller onto the deck, like the local positioning system talking to the ultra-wideband chip is pretty chatty. There's a lot of communication back and forth. This could be improved by doing this short communication then on the deck and then sending more processed data from the deck to the Crazyflie. Another one then is the deck combinations as well. Same thing here. Some decks we might be able to move a functionality from a very wide bus like the SPI that takes like the SPI pins plus chip select one to something more like I2C where we can have a lot of devices on the same bus, saving up a lot of pins. But still, again, here we might have to process the data on the platform, so we read it out from whatever's on SPI, for instance, process it, and then make it available through I2C to the Crazyflie, saving some of the pins. Having a microcontroller on the board also might make it possible to switch pins, to have multiple buses. The last one, of course, then the MCU on the DEX. This will, of course, be even worse when we start moving and having microcontrollers on the DEX. So here there needs to be some improvement. And the proposed solution for this is 2 parts. So the first part is hardware that would need to be added. So here is a quick sketch of the proposed solution. So one of the problems we have today is that we don't have so fine-grained control over the microcontrollers on the DEX. So for instance, it's not possible for us to reset one deck at a time. Instead, we need to repower. We need to shut off the STM and the switch that goes to the expansion decks, and then repower it again if we want to reset things. Or we need a pin for every deck to reset it. And I mean, this quickly becomes problematic because if you have a few buses, you have a few pins to reset and so on. It's hard to make this fit with the pins. So the idea is to put a small microcontroller, basically an I2C GPIO extension on the DEX. So it's on the I2C bus, so we can have a lot of them. And the idea is then to be able to control this, to say like pull this pin high, pull this pin low, and then connect these pins to the other electronics on the board, like the power regulator. So being able to shut off a deck by just saying, okay, pull enable high or low to shut it off, or various bootstrap pins like for the ESP today The AI deck has an ESP on it. And there's 2 pins to bootstrap. You need to program it. So you need the reset pin to be able to reset it, and you need the boot pin to pull, and then you need the UART to supply the data. So this is 4 pins just for the bootload. Sure, you can reuse the UART for the normal application as well. But the idea here is to save some pins. The other part of this is then the main MCU, like I said, connecting to multiple buses. So then the idea would be that you would connect it to both UARTs, for instance, and then either you could bootstrap it through this little microcontroller by pulling one pin high or low, and at startup you know which buses you can use, or you communicate with I2C saying like, okay, you can use UART1, and then you can power on the next deck, and you say, okay, now you can use UART2, for instance. This is of course more complex, but it also gives more power to us to be able to control the decks and and handle like this more complex situation. The other part is of course the software to do this. So one of the things that we've been discussing a little bit is the bootloading. If you put microcontrollers on the deck, you need to be able to bootload them. You need to be able to update the firmware. And the idea is to use the built-in bootloaders. So this is what we do today with the AI deck. We use the ESP bootloader over UART. We have a lot of ST microcontrollers. They have something called DFU, where you can upload new firmware to it. So you don't actually have to build the bootloaders for this. But for this to work, you need to basically power on each deck at a time to bootload it, which then again is reliant on this hardware solution. Yeah, exactly. And the last one here, pin sharing from the previous slide. Also being able to do this needs some software. So you need to be able to tell the decks like, okay, use this bus, do this, do this. And then the 2 ones in the middle, communication and development. So for the communication, we need to be able to talk to these decks when you put the microcontroller on it. Today, for the AI deck, we have something that we named CPX, Crazyflie Package Exchange, I think it's called, named after. Where the idea is that it's possible to send like data from the STM to the AI deck's ESP, to the AI deck's GAP8, and use the Wi-Fi to reach the computer. So there needs to be a system where the decks can send data to the Crazyflie back and forth in an easy way, and not having to reinvent the wheel all the time. Minimizing the impact on the Crazyflie for each new deck. So if you add a new deck, there shouldn't be too much work you need to put in, like for special messages for this deck and so on. And the last thing that we don't have a solution for, even a proposed one, is like the logging and parameter framework. So today, something that's really powerful and useful on the Crazyflie is the logging and parameter framework. So basically in C code, you tag a variable saying like this should be loggable or this should be settable, and then you can set it from the ground. But if you start moving functionality out from the Crazyflie onto the decks, they're kind of disconnected from the system. And it would be really good if you could reach them somehow to have the same functionality without having to re-implement it on the Crazyflie. So the option would be to pull in data onto the Crazyflie and then log it. But this would then require, like for every deck, you would have to add code. And this is something we would like to avoid. But last but not least, there's also some bonuses, which isn't really part of what we need, but also nice. So one of the bonuses with this solution would be that you can shut off the decks individually. So imagine if you're flying around, you have AI deck and you have a lighthouse deck. When you're landed, you might not be so interested in the position anymore, but you're very interested in having the AI deck to look with a camera, for instance. Then with this system, it will be possible to shut off the shut off a lighthouse deck until you want to fly again. Then you can turn it on again. I mean, you could also turn off the AI deck if you don't want this, and then you could fly only using the lighthouse. Another thing that we've been discussing, this is very iffy, is it might be possible also with this idea of being able to say this deck should have this bus and this deck should run on this bus. It might be possible to have two of the same deck. Not really sure why, but maybe there will be a reason at some point. It also potentially same, like at the same time as we solve this, we also solve like the problem of the inter-deck communication to the Crazyflie, but also how we handle decks with Wi-Fi, for instance. So today, I mean, today we use CPX for the AI deck, for instance. So when you put on the AI deck, you can use CPX to communicate through the AI deck with Wi-Fi to the Crazyflie. But this doesn't look the same as when you connect with the RTP to the Crazy Radio, for instance. There's some bridges that we've made here. Like it's possible to send commands through Wi-Fi through the AI deck to the STM. And if we solve this problem with communicating between the STM and these MCUs, maybe we at the same time also solve this problem of having, when we add decks with different capabilities for communicating on other channels. Maybe we can use the same solution for this. Yeah, and I think that's it for me. This is the end. So if there's any questions, comments, discussions, anything.
And if you want to, you can write the questions in the chat, or you can turn on your microphone and speak.
Hi, I'm absolutely agree that we might need to add some microcontroller onto the deck. In fact, recently we are doing some experiments, and in our experiments, we use a lot of lock deck and also the flow deck. As you just said, both decks, they use SPI. So we, in our scenario, in our application scenario, the lock deck is very busy. It receives and transmits a lot of data. So the two decks, they are competing for the SPI, and we got a lot of problem, and our Crazyflie cannot fly very stable. So I'm absolutely agree that it might be a good idea that some microcontroller on the lock deck may handle the data transmission and offer the processed data to the STM, and I do think it is a very good idea.
Yeah, thanks. Yeah, and yeah, and but are you using TDOA or two-way ranging?
No, we design our own protocol. We design a protocol that is a swarm ranging protocol, and in fact, we also post a blog on our as a guest blogger and at our blog. So
nice. Okay,
yeah. In fact, I can show some data we get from our experiments. Let me see if I can show my screen. Okay. It's the first time I use Google Meeting.
Yeah, this I'm not sure. Yeah,
I'm not sure. Yeah. I'm sharing. Okay. Okay. Can you see my screen?
Yeah.
Yeah. In fact, we recently we designed a new, not really a redesign. We just update the DW1000 module to DW3000 module. They look like this, and we did a lot of the driver scenes, and we move all the driver onto our Crazyflie. It works fine, and you can see the DW3000 has more stable measurement. So yeah, this is what we do about the driver. And my problem is I'm very interested at the processing delay. So according to some documents, I decompose the processing delay into 3 periods: the IC period, the IRQ period, and the SPI period. So you can see each time we receive or transmit, there are 3 periods that each of the periods have some time, some sort of time. And according to our experiments, we have some estimated time here. So if we have very short byte to transmit or receive, the IC, okay, let me go back. The IC means what the module, the DW3000 module used to transmit or receive time, and to receive data. Once the data is ready, the DW3000 will issue an interrupt and tell the STM to prepare for the data, and the STM will have this amount of time for the preparation, and then the SPI starts to actually transmit the data. So it's IC, IRQ, and SPI. And according to our experiments, if the data is very short, like 28 bytes, the IC has 0.17 milliseconds, and the IRQ 0.13, and the SPI we try some different speed. If it is at 2 megahertz, that is a default speed. It takes like 0.42 milliseconds, and if we speed up and to 21 megahertz, it's like 0.04. And however, if we have a lot of data to transmit, like we have 220 bytes, then this time goes up very quick. So at this time you will the local deck will have the SPI occupied, and the flow deck will have no chance to have to wait for the time to pass and get its own chance to transmit data. So that is what I want to show.
Okay. Yeah, but I don't know. Maybe the others will have to correct me here. But I think that once the transmission won't be preempted, right? I mean, if you start the transmission, you will have until the end, right?
Actually, we can interrupt.
Yes, it's nodding. Yeah. In the implementation we have now, but like if you start communication, if you take the bus by pulling chip select, then you have a bus until you release.
Yes, I think we have some issue to coordinate the use. They have they will take let me see. Yeah. Okay. Actually, recently I'm thinking about myself build another log deck that combine microcontroller like ESP. We have some. We already have a successful ESP application on AI deck. We we also did a lot of research on the ESP. It seems very powerful. So myself is thinking about building a deck. You know, we have a lot of UWB communication. So if we have dedicated microcontroller, it will be very useful.
Yeah, I think so. I think that, I mean, the kind of problems that you're talking about here is one of the issues why we've been discussing this proposed solution with moving microcontrollers out. I mean, to some degree, I mean, then you still need to communicate, and you might still need data from a Crazyflie and so on. But yeah, I mean, this is one of the reasons.
And
But I mean, if that's right.
I would say that the big benefit is that we only need to communicate high value data between the deck and the Crazyflie, as opposed to talking directly to a sensor, which might need a lot of just a lot of messages that are not that high value. So I would say that this is one of the big advantages of having a dedicated CPU on the deck.
In my opinion, if we add a microcontroller to deck, it will help. However, have you considered to update Crazyflie? You know, Crazyflie have NRF for wireless communication, right? And it seems that ESP has equal functionality, and it has more power for more speed and more memory. I remember it have 500. So, have you considered to upgrade Bitcraze?
Crazyflie to this, yeah. I mean, I think this is we've discussed this definitely. Yeah, I think one of the problems we come back to is how to enable really low latency communication. So with and how to control this. So with the Crazy Radio, for instance, since we have a dongle on the PC side, and we have very low level control as well on the Crazyflie side. We have like a controllable latency in between. We control this chain very well. So the latency is lower than Bluetooth, for instance, and it's much lower than Wi-Fi, and it's also more consistent. But one of the things that we've thought about definitely is VSP. I mean, having Wi-Fi would be very nice.
Okay, then I agree to focus on updating deck on deck. Thank you.
Yeah, thank you.
As a sort of a comment to this as well is that this one of the reasons that we're thinking about how to work with the expansion bus and decks and so on is to have some sort of future-proof solution, or maybe for a future Crazyflie or whatever it might be. I mean, if we change the deck structure or if we improve it, we want to have something that is future-proof as well, of course. So this is a very good comment that maybe improving the Crazyflie itself.
Yep. Any other questions or comments? Nothing. Aye, but then maybe we're done. And
thank you very much, Marcus.
Thank you
for the discussions. We will now turn off the recording. So for